So today I'll go back to talking about how balloons work. One thing, so we'll finish up with the balloons today and do a lot of water distribution next time. The problem set, which is due on Friday, needs some of the water distribution discussion, so I think I've got it timed okay. I accidentally mangled question 9 in transferring it into the homework site. I fixed that, but if you got caught, there are very few people who have tried to answer it yet, but if you got caught trying to answer it and got some random score, write me an email and I'll ultimately fix it. All right, so the story at present is balloons. Ultimately, why do certain balloons float? Balloons full of hot air can float, and balloons full of helium can float. Balloons full of air don't float. I guess in general, what's floating and why? And leading into that then is the story of pressure and fluids like air, all the gases, all the liquids. Fluids push by way of pressure rather than pushing by way of simple force. They're not totally different. They're totally related, in fact. But since fluids don't have a fixed point at which they push on surfaces. And so the forces are typically described not in terms of the total amount of force, but the amount of force applied to each unit of surface area. And the SI unit of surface area is the square meter. It's big, for better or worse. And the atmospheric pressure, the pressure that we're in right now, pushes on surfaces quite hard. It pushes with about 100,000 newtons on a surface that's a meter squared. So it's about 100,000 newtons per square meter is our world of pressure, and we abbreviate that newton per square meter as the Pascal. So we're immersed in a fluid that's pushing on us with a pressure of about 100,000 pascals. Any questions about the idea of pressure? All right. We're used to, with objects that are being pushed on by multiple forces, we're used to sort of adding up the forces, taking into account their direction, to see what's the net force on the object and therefore how it accelerates. With pressure, instead of adding up the forces, we look at the pressure and the surface it's pushing on. And in so many cases, what really matters is the imbalances in pressure between one region that's exposed, of an object that's exposed in another region. For example, this sheet of paper right now is experiencing essentially no pressure imbalance. Why? Because the pressure on its left side is the same as the pressure on its right side. So although the left side is being pushed to the right quite hard, the right side is being pushed to the left quite hard, and the net force on the paper is pretty much zero, at least due to air pressure. If it weren't like that, if there were high pressure on one side, low pressure on the other side, then you get a pressure imbalance. Just as sort of jargon, I guess, but that's the idea. And now there are significant forces on all the parts. So I showed you pressure imbalances last time. If you do stuff like take the air out from inside a container, you have air pressure pushing in on it, but no air pressure pushing out on it, and it gets pushed in very hard. There's an inward push on these surfaces, and it's hard to pull them apart. All right? A last thing to point out is pressure imbalances can push on air itself. So if you have high pressure here on the left and low pressure on the right, the air in the middle, it's an object too. It will be pushed, and it's always pushed towards lower pressure. I mean, if you just think about it, high pressure pushes harder towards the low pressure, then the low pressure pushes toward the high pressure. And so there's an overall push towards lower pressure. And we'll see that in the absence of gravity, which sort of complicates the story, fluids tend to accelerate towards lower pressure. It's just it's a pretty much a general rule. I mean, it's probably I got to be careful about it, but it's the basic idea. All right, so one thing I should say before going too far into this, looking at the little tire, the tires here full of cartoon air molecules. You know, where does pressure come from? In air or any gas, pressure comes from the relentless collisions of the little teeny air particles, both atoms and molecules, hitting surfaces. They're just peppering the surface. So any surface you like, this sheet of paper, it's being hit with a fantastic number of air molecules and atoms bouncing off it. I'm using the words atoms and molecules casually too. You all have bumped into those somewhere along the line. Most of the particles in the air are molecules, the most abundant of which is nitrogen. Surely you know about nitrogen and oxygen. Nitrogen as atoms, nitrogen atoms are rare in the air because they love to pair up. So most of the nitrogen, essentially all the nitrogen in this room as air is in little molecules that consist of two nitrogen atoms stuck together by a chemical bond. And the same is true with oxygen. It's not as common as air, as nitrogen, but oxygen's around as pairs of oxygen atoms, with rare exception. And then everything else is kind of small potatoes. We'll see water is also part of the air. It's usually left out on the tables that you may have learned way back when. You know, nitrogen's 79%, oxygen's like 20%, and then all the rare ones, carbon dioxide, argon, neon. They leave out water. Water is kind of a variable constituent in water. In air, it depends on the humidity, and we'll talk about humidity later on in the semester. But right now, it's a pretty humid day, actually. So they're about 3%, 4% maybe of the particles between us right now are water molecules. Don't ignore them, they're significant. Okay, so they're bouncing like crazy off of any surface. And in contrast to macroscopic, visible objects like bouncy balls, the particles, these atomic scale particles can bounce perfectly. And they do approximately. It's a little more complicated than that, but they're bouncing. They hit, they rebound, they do all the stuff we've seen before. If the surface doesn't move, they can't do work, but they do transfer momentum and all that stuff. And that's where the force comes from. It's from this relentless. I'm now looking at the wall. Imagine these particles bouncing off the wall. I've shown you already that if I throw a ball against the wall and it bounces back, it gives approximately twice its forward momentum to the wall. Right? So if you look at how many particles hit the wall, they're not very big, but each one gives a little bit of its momentum to the wall. If you look at the momentum transferred every second, and you divide by the second, you get an overall force. Because, I mean, I'm saying this too glibly, but remember, the transfer of momentum is force times time. The time part is a relentless, ongoing thing. And so there's a force that's involved. And the many, many bounces of these particles against the wall averages out to a steady force that depends on how big the surface is and therefore how many particles hit it. And ultimately, when the dust settles, you get this pressure, this steady pressure, because of this relentless bouncing of tiny particles off of surfaces. We could go on forever about it, but hopefully that made some sense, and it's enough. In liquids, it's a little more complicated because the liquid particles actually cling to each other. The particles in a gas are simpler because in principle, they're just independent little bouncy balls, bouncing off things. All right? Okay, so about air, just to look at the tidbits I've got on my slide here. The air's density. What is density? I told you about pressure. It's the force exerted per unit of surface area. And we use pressure to deal with fluids because forces are kind of inconvenient. They don't sort of behave right to apply simple forces. The same thing goes for mass. Objects have a simple mass. The object of my laser pointer. Yeah, my laser pointer has a certain mass. Life is simple. How about the mass of the air? Well, the mass of the air depends on how much I have in mind. So if I have a little bit, of course, it's got a small mass. If I have a lot in mind, it's got a bigger mass. How do you deal with that? Well, with gases and basically any fluids, liquids included, the way of characterizing sort of how much mass it has is by figuring out how much mass it has within a certain volume, the mass per volume. How much mass is there in a liter, or in a gallon, or in a cubic meter, something like that. And air, it turns out, has a mass of about 1 1/4, that is right around here. This air, I should be careful, not any old air, not air up in the stratosphere. The air down here has a mass of about 1 1/4 kilograms per cubic meter. So if I could chop out a chunk of air about this, and this, and try to shake it, it would be kind of like shaking a 1 1/4 kilogram sack of flour. It's got that same mass. And consequently, it's got a weight, and the weight, it's 9.8 newtons per kilogram. It's got a weight of about 12 newtons, 12 apples, little apples. Okay? So that's density. Density measures mass per volume. It's not weight per volume, it's mass per volume. The density of water, much higher. Density of water is about 1,000 kilograms per cubic meter, which is the same. You know what's a liter? You're used to liters. You're not used to cubic meters. A liter is 1/1000th of a cubic meter, just a simple thing. So a liter of water has a mass of about 1/1000th of a cubic meter, or about 1 kilogram. So a liter and 1 kilogram go together. A liter of water and 1 kilogram. And so many things have about that same density, that same 1 kilogram per liter. It's just sort of a useful one to know. All right, that's the concept of density. You okay with the concept? Any questions on the concept of density? To put things in perspective, you've seen air has a very low density, 1 1/4 kilograms in an entire cubic meter. Water has a much higher density, about 1 kilogram in a much smaller volume, a liter. Things that you're familiar with as relatively heavy or dense, mercury is about 14 kilograms per liter. It's about something like 14 times as dense as, maybe it's 11 or 12. It's up in that territory, and it's getting almost as high as you get for density. I'm avoiding solids, but they also have density. Same idea. Yeah. Yeah. Okay, the pressure in a balloon. So I do a balloon like this. It's not filled with ordinary air quite. The air inside it has a slightly higher pressure than this outside air. So this is atmospheric pressure by definition out here. That's a little above atmospheric pressure. So far, is that okay? The reason, why would it be above atmospheric pressure? Well, it's above atmospheric pressure because it needs to there needs to be a slight pressure imbalance across the balloon skin. The balloon skin wants to get smaller. It's pulling inward because of elastic forces in the skin. So to balance those forces, the air actually has to have a net outward push. And that comes about because the pressure inside the balloon is a little higher than the pressure outside the balloon. Is that addressing the question? And associated with that higher pressure inside the balloon, you all okay with the idea of a higher pressure inside the balloon? You'll know of this when we pop I'm not going to pop the balloon. If we pop the balloon, there's a kabang, right? What's happening is I suddenly released high pressure air in the middle of ordinary pressure air, and there's an abrupt pressure imbalance sort of released on the environment, and everything jumps outward accelerations, and that ultimately sends sound towards your ears. And the bigger that pressure imbalance is, the louder the sound approximately. So that's why firecrackers or something like that have a tremendous pressure imbalance when they burst. The pressure builds up inside this container, bang, the container opens. And out comes this pulse of pressure. So there's a higher pressure inside. It's modest. Where does it come from? It comes from the air inside there is a little more dense than the air out here. There is a relationship between the density of the air, all else being equal, which we'll see all else includes temperature, the denser the air is, the higher its pressure is. And that isn't, understanding why that's the case isn't very complicated. If you've got more air particles packed into the same space as before, they hit every surface more often. They're just more bouncy balls skittling around inside the container, and they hit more often. The same impacts, but suppose you double the density of air inside here, meaning you pack twice as much mass inside this balloon, twice as much mass of air. Well, that means you actually have put in twice as many particles as before. They go together. The density of air, if you double the density of air and you look in a liter of it, it has twice as many particles as it used to have. And therefore, they hit the walls twice as often. And therefore, they hit the same way as before, so you double the pressure. So a first simple observation, this is sort of a piece of what's known as the ideal gas law, which you probably also have bumped into somewhere along the line in a chemistry class. Some colleagues and I were chuckling about the fact that teaching the ideal gas law in chemistry is a little bit oxymoronic because the ideal gas law assumes no chemistry. It assumes the molecules don't care about each other at all. No interactions. Anyway, that's physicist humor. The point of this is, one of the pieces of what I'll eventually come up with as the ideal gas law is that if you double the density of a gas and do nothing else about it, so it's the same gas just packed twice as tightly as before, its pressure doubles. So the pressure is basically proportional to density for a specific gas like air. And it should make reasonable sense. It's just a matter of hitting more often. The more you pack them in there, the more they hit. Okay, so we've got slightly densified air inside this balloon. That's why it's got that pressure. All right. Well, that brings us to the atmosphere. So I told you the pressure down here being like near the Earth's surface as opposed to way up in the sky. The pressure down here is about 100,000 pascals. It's a little more than that. It depends on the weather, the barometric pressure and so on. As the pressure, yeah, that's good enough. So why is it here? The pressure down here is as high as that because of gravity and because of the weight of the air overhead. If there were no gravity, if we turned off gravity somehow or other, the Earth's atmosphere would go away. And this happens to small planets and things like the moon. The moon may once have had an atmosphere, but it lost the atmosphere because gravity wasn't strong enough to keep the gas particles on its surface. The Earth has managed to cling to its atmosphere for rather a long time. It has lost the tiniest of its particles. I told you about nitrogen and oxygen being the little molecular things that make up most of the Earth's atmosphere, and water, which is also part of the atmosphere. There are, in very small amounts, a couple of other things, one of which is familiar to you, is helium. The helium is an atom. Helium atoms interact with each other so weakly, their chemistry is so minimal that they stay on their own. They're one of the noble gases or inert gases. The other ones that you're familiar with are neon, argon. There's some rare ones, krypton and xenon. But those guys don't cling, they don't pair up. They remain inert and little lone particles, they go around. The helium particles are so dinky and light that they actually can essentially evaporate from the Earth's atmosphere. And so they become very rare in the Earth's atmosphere. Hydrogen, similarly. Hydrogen is, given its choice, would be a molecule. It's rare to find a hydrogen atom. They like to pair up, just like nitrogens and oxygens. But the hydrogen molecule is still so tiny and light and fluffy, it manages to escape the Earth's atmosphere. And so we don't have there's not much hydrogen in the Earth's atmosphere as hydrogen, and there's not much helium as helium. It's rare. Public service announcement, we'll play with helium here. Helium that you play with comes from natural gas wells. It's not taken from the air because it's so rare in the air, it's not cost efficient. It's taken with natural gas, And that's a limited resource, meaning once it comes out, you can't get it back. And this will be an issue probably in your lifetimes, that helium will start to become oh my gosh, we wasted it making toy balloons. Oh my goodness, it's now really hard to come by and very expensive. So with luck and good fortune, I guess that's the same thing, it won't happen in your lifetime, but maybe your children's, it's going to happen eventually. Helium is going to become precious as opposed to fun and games. Okay, back to the Earth's atmosphere. The Earth's atmosphere is held in place by gravity. No gravity, no atmosphere. So all the air is being pulled down towards the Earth's surface. Every little particle there has a weight. When it's not hitting anything, so when it's most of the air molecules, they spend most of their time not hitting anything. While they are not hitting anything, they're little falling objects. They follow the same rules we're used to. They travel in the arc of a falling ball. They happen to be going very fast. First off, why are they going fast? It's because they got thermal energy. The energy associated with temperature, that random energy, here at room temperature, they've got each one has a statistically distributed amount of energy. And because these guys are independent, it's primarily in the form of kinetic energy. So they're whizzing around. They're really whizzing. Their particles of nitrogen and oxygen are traveling about 300 meters per second. 300 meters, that's a meter. 300 of those things per second. They're going really fast. They're going hundreds of miles an hour. I should know that. It's probably about 700 or 800 miles an hour. It is not. It is the speed of sound and that speed are related to each other. So they're going really fast. They don't go very far because they hit each other so often. So they're skittling around like crazy, making very little progress because they're bouncing off each other all the time. The fact that they're skittling around with that, like that, you're aware of this in an indirect way. That skittling is statistical, and so they gradually make progress from one place to another. So if you release a gas that's not the same as everything else, for example, open a bottle of perfume here and release some molecules that are not ordinary air molecules, that jittering around, bouncing off each other, will cause them to gradually migrate, what's really called diffusing. They'll diffuse through the air gradually, and after a certain amount of time, they'll have drifted over to somebody across the room, and they'll go, oh, I smell it. So these are indirect indications of this statistical motion of tiny particles due to their thermal energy. Okay, so the point of this is the particles are moving like crazy. They don't all glom onto the surface of the Earth and sit there like lumps. Because of this statistical thermal energy that they have, they bounce off each other and they kind of lift themselves off the surface of the Earth. Gravity is pulling them down, but packing them very tightly like that would have them bouncing against each other so vigorously that the pressure would rise enormously, and that pressure will lift the top ones upward. They'll accelerate upward, huge upward pressure imbalance. And so the atmosphere kind of lifts itself off the Earth. I mean, this is apocryphal. I mean, it happened, it never really happened like this, but you can imagine. If we tried to pack all the air molecules down there on the surface of the Earth and gave them all this thermal energy, they would lift off, lifted by the tremendous pressure imbalance between the high pressure where they're all packed too tightly and hitting each other like crazy, and the lack of pressure above them. Up they go, and the atmosphere eventually settles down at equilibrium the way it is. And the way it is the pressure down here is high because it needs to support the weight of everything above it. So if you imagine a cube of air down here, I won't make it, actually it shouldn't be a cube, rather a square box of a certain height. And let's put 1 kilogram, right? In my drawing I've got 1,000 kilograms of air, but I can just say 1 kilogram here. There's a 1 kilogram box sitting here, and what it has to make sure about is that the pressure it exerts on the top of the box, which is sort of an invisible surface here, is the same as the pressure that the stuff up here exerts on the top of the box in the opposite direction. Those have to balance, and where does ultimately the pressure that the stuff up there exerts down here come from? From its weight. It's in equilibrium. So gravity's pulling it down with its weight, and it must be supported by the air in my box pushing up. So for it to be all at equilibrium, the pressure in my box has to be enough to support the weight of that whole column of air. If I look at a second box up here, sitting on top of the first box, it's in the same boat. It has to push up on its top surface enough to support the weight of all the air above it. But there's not as much air up there, right? Because this box is higher, and it doesn't have its own weight above it. So it pushes a little more gently on that box because there's less weight overhead. And if we go up to another box, it pushes up to support the weight of all the air above it, but it doesn't have to support its own weight anymore, and so on up. And the point of that little story, it's like Yertle the turtle. Is that still, you don't want to be the turtle at the bottom of the stack. I guess you don't want to be the turtle at the top either. But with every box sitting on top of the other, the pressure goes down a little bit, because you only have to support the weight of what's above you, not what's below you. And as you work up the stack, it's just not as much. Associated with having to support less and less and less weight, and therefore have lower and lower and lower pressure, is the density goes down as well. Because remember, pressure and density are best friends. So if the pressure up here is less than the pressure down here, the density up here is less than the density down here. They go together. And so this sort of approximately explains your experience, say, going up into the mountains. You feel your ears pop, or an airplane. You feel your ears, something's funny in your ears. If you go into the mountains, breathing doesn't do you quite as much good as you're used to. People who have trouble with oxygen, getting enough air, struggle in the mountains, may not be able to go into the mountains. That's because the higher you go, the thinner the air gets. It has less density, it has less pressure. And by the time you're 10 kilometers or so, or 20 kilometers up, there's not a lot above you anymore. The air's running out. It's actually a very thin layer around the Earth. The Earth's so big that if you sort of see the Earth on scale, the atmosphere is just this thin film on its surface, clinging there because of gravity, but not settling because of thermal energy. Questions about the atmosphere structure and why it's like that? Okay. A key feature of this observation is there is the pressure and density, they go together, they're decreasing with altitude. And that's certainly true on the scale of mountains and going in plains and all that, but it's even true here in this room. The pressure down low near the floor is a little higher than the pressure in the middle of the room, and is certainly higher than the pressure near the ceiling. There's a continuous variation in pressure, getting less and less as you go higher and higher just in this room. That's described as a pressure gradient. I've used the word gradient from time to time. Gradients are smooth variations in physical quantities with position. So if we go from red to blue, that's a gradient in color. This is pressure going from high pressure to low pressure. That's a gradient in pressure. And the official directions of gradients are towards the most rapid increase in the physical quantity. So officially, the gradient is a downward vector pointing towards the higher pressure. But that's not so important. What's important is this is what supports balloons. It's that pressure gradient that's present in the Earth's atmosphere. It's pressure actually in any fluid in the Earth. Water has the same experience, that the water at the bottom of a tank has to support more weight than the water at the top of the tank. So the pressure at the bottom of the tank is higher. And because water is so dense, that pressure gradient is big. The pressure varies very rapidly with altitude. Oh, that's okay. So why does a balloon push up? Why does the atmosphere push up on a balloon? It's because even for this little teeny thing like a balloon, the pressure at the bottom of the balloon is a little greater than the pressure at the top of the balloon. And that means that the atoms and molecules up here skittling along and bouncing off that surface. They push down on every square portion a little more gently than the atoms and molecules at the bottom, skittling around, hitting the bottom surface. It's denser down here. More impacts per second on every square centimeter, say. And so the bottom's pushed up a little harder than the top is pushed down. There's an imbalance in force overall on this balloon. It's being pushed up a little bit by the air. You okay with that idea? It's weird, but it's true. If you put this in water, that effect would become much more dramatic because the pressure, we're underwater now. The water here is pushing up. It's not quite the same dynamic motion here, but it's pushing up considerably harder at the bottom, much higher pressure here, noticeably higher pressure down low than up here. So the upward push at the bottom is considerably bigger than the downward push at the top. And the balloon really has a strong upward push because of the surrounding water. Yeah? Is that similar to how buoyancy works? It is exactly buoyancy. That is buoyancy. This is all lumped together. It's here at the bottom. It's the buoyant force. The name for the overall force on an object like this, due to the imbalance in pressure around its surfaces, the name for that is the buoyant force. It's a real force. So I asked you, I told you early in the first day or second day, when I throw a ball up in the air, and I said, is there a real force pushing up on it? And I'm pretty sure I said neglecting any air effects. I should have in any case. If you include the air effects, there is a real force pushing up on it, the buoyant force. And it's just due to this imbalance of pressures around the ball or the balloon. You okay with that? Those are the same thing. The pressure imbalance force and the buoyant force, same thing. It's like weight and the force due to gravity, they're the same thing, just two names for the same thing. One of the great questions then is, so how strong is the buoyant force? It turns out the buoyant force, you can determine it very, very easily. It's known as Archimedes Principle. It's a sort of an amazingly, it works, just works. It always works. I have specific things in mind, the special cases to consider, but the force that this balloon is experiencing in the upward direction due to the pressure imbalances around it, in other words, the buoyant force it's experiencing, is exactly equal to the weight of the air it's pushing out of the way. So it displaces is the word they use it. So picture, there's the balloon, see it? Picture that shape, and now let me take the balloon away. And here it's my left hand, it's on your right, but there is still a balloon-shaped blob of air there. Can you see it? That balloon-shaped blob of air has a weight. And that downward weight of that balloon-shaped blob of air weight is exactly equal to the upward buoyant force this balloon is now experiencing. Now, why is that? The reason for that perfect match of forces is because if I take the balloon away, there's the balloon-shaped blob of air. Here it is, right? It's at equilibrium. It's not accelerating anywhere. It's just sitting there. It's a calm room. There's no air blowing here, okay? And it's sitting there not accelerating. Therefore, it must be experiencing zero net force. Okay, if that's true, it's experiencing, I can think of two forces it's experiencing. One is its weight, downward. So something must be pushing up on it with a force that's exactly equal in amount to its weight, but upward. And that something is the surrounding air, pushing up with a buoyant force. There's a buoyant force on that blob of the balloon-shaped blob of air, even though it has no skin, it's just there's no film around the outside, it's just the air itself. That portion of air is being pushed up by the surrounding air with a force that exactly equals its weight. You okay with that idea so far? If I now scoot that air out of the way, get out of there, and I put the balloon in its place, The surrounding air doesn't care. It's oblivious to what it's pushing on. It's pushing on something in the middle. Whether it's a balloon-shaped blob of air or the balloon, it pushes the same, exerts the same force, same buoyant force. So the buoyant force on this balloon is equal in amount to the weight of the air in that balloon-shaped blob. And that's the logical thought process that gives rise to Archimedes' principle. So this balloon displaces, 5 grams, maybe not even that, 1 gram of air, and it experiences a buoyant force of 1 gram upward. So, I'm pulling numbers out of thin air. Oh, not unintentional, stupid pun. Okay? If we do it in water and displace water with this balloon, it displaces a much more weight of water, and that's why it gets a much stronger buoyant force. You guys are currently displacing some 100 grams maybe of air, and so you're experiencing like about 100 gram upward buoyant force. To give you one of the crazy cases that's going through my head is, suppose you take this balloon and you immerse the bottom half in water and the top half in air. You basically put it at the interface between water and air. You take it into the bathtub and pull it down like that, and your roommates go like, "You're crazy." Okay. It's experiencing an upward buoyant force that's equal to the weight of the 2 fluids it's displacing. Part of it's displacing air, and it gets a small buoyant force for doing that. And part of it's displacing water, and it gets a small buoyant force for displacing that as well. And if you pull it deeper, so it's displacing less air, more water, the buoyant force goes up. If you lift it so that it's displacing less water, more air, the buoyant force goes down. And this is why when you throw objects that sort of float at that interface, like a piece of wood, you throw it in the water, it bobs up and down a little while trying to negotiate, whoa, where's the right depth where I am displacing just the right mix of water and air to support my weight, and that's where it settles. It settles at just the right height where it's displacing just enough water, just enough air, that the buoyant force on it is equal to its weight, and it's in equilibrium. Okay? And there are a million interesting examples of that, and you'll see some of them on exams. All right. So, having done that then, we can look at the balloons. Boy, I'm burning up time here. So there are 2 ways to make a balloon that has more buoyant force than its own weight. So I mean, look, I should say this. This balloon, when I let go of it, will slowly descend towards the floor. Part of that slow descent is wind resistance, air resistance, which we'll come to. The other is that it's not just experiencing its weight. It's not just a falling object. It's experiencing its weight down and a buoyant force upward. And they do a pretty good job of canceling. Not quite, but basically there's a very small leftover downward force, because this, alas, weighs more than the air it displaces. For 2 reasons. One, it's got some rubber in it, and the other is that the air inside is a little extra dense. So it's got sort of a double problem. It just has more weight downward than the air it displaces, and as a result, it's big weight down, little buoyant force up. There's a net overall downward force on it, and when I let go, it starts to accelerate downward. Okay with that? If I want a balloon that won't do that, that will accelerate upward, I need to make a balloon that is lighter than its own buoyant force. And there are 2 ways to do that, 2 easy ways. One of them is to put air inside the balloon, but use less air. And how do you do that? Heat the air up. If the air is hotter, that means it's got more thermal energy in the same number of air molecules. They travel faster. That means when they're traveling faster, they hit more often because they come into any surface more often, and they hit harder. And it turns out that the pressure that the air exerts is proportional to its temperature, but on a weird scale. I got too many things to say in too little time. If you double the temperature of air, and I'll come back to this, what doubling means, the particles are traveling faster, and it all works out such that the pressure doubles, assuming that the molecules have no interactions, what's called the ideal gas situation. You okay with that basic idea? Hotter gas, there's more collisions with any surface, they hit harder, the pressure goes up. Temperature. Doubling the temperature, you got to double it on the right kind of scale. You have to double it on a scale where 0 really means there's no energy left, no thermal energy. Associated with temperature is thermal energy. And it turns out the thermal energy, the average, and specifically it's the average thermal kinetic energy of the gas particles. That's the average statistical dose of kinetic energy that every particle has because of temperature. That's proportional to temperature. So the temperature you've been measuring your whole life, you're measuring variations in the average thermal kinetic energy in the particles that are present. To find the 0 of temperature, in order to double something, you got to know what 0 is, so that you know that you're this much above 0 to start with, and you're going to double temperature, you're going to go to this much above 0. So what's the 0? It's not the 0 on the Fahrenheit scale or the 0 on the Celsius scale. It's the 0 of any scale, what's known as absolute 0. And absolute 0 is cold. On the Fahrenheit scale, it's about minus 459 degrees. And on the Celsius scale, it's about minus 273. There is a scale that is very similar to the Celsius scale that has the same spacing between 1 degree Celsius is the same as 1 Kelvin step. Same step, the steps are the same. But the 0 of the Kelvin scale is the real 0, absolute 0. Anyway, what I want to do is I want to show you, let's get part way to absolute 0. I can't go all the way to absolute 0 for many reasons. We can go 3/4 of the way. So this is liquid nitrogen. My general rule is any excuse for liquid nitrogen is a good excuse. So this is the same nitrogen you're breathing right now. It has been liquefied. We'll see, in effect, how to liquefy it a little later in the course. But from its perspective, it's just a normal liquid, except that it boils at a very low temperature. It boils at it's about minus 300 Fahrenheit. So it's pretty cold. And I poured it into a glass container, and that glass container, from its perspective, was way, way hot. So this should put us up. Yeah, okay. So it's still boiling. It still thinks the room is awfully hot, and so it's still boiling. This container here has vacuum in between the two walls. It does a pretty good job of keeping thermal energy from going in and making it boil. But it's cold, all right? And if I put air in there, an air-filled balloon, well, I'll start with the air-filled balloon I've been playing with. Some of these demonstrations will have to come back on Wednesday. That's just life. All right. So if I put this balloon in, I'm going to slow down that thermal molecular motion of all the particles. They're going to push less hard on each other as a result. They're just traveling slower. And the balloon, the outside air pushing in, will have not as much pressure pushing out. The balloon is going to shrink. Okay? Little shrunken balloon. I should show you first, I should do this with helium. So this is a helium-filled balloon. And if I put this balloon in, and I cool it down to about 1/4 of its original room temperature, which is what I'm doing, the pressure will go down by about a factor of 4. And we'll have to, what's going to happen then is the balloon will shrink, and the helium atoms will get packed about 4 times as tightly together as before. The density is going to go up by about a factor of 4 in order to summon up the same pressure. So the density times the temperature is going to stay the same. Temperature goes down, density goes up, the pressure will hold the same. So there's the helium-filled balloon. And incidentally, the helium-filled balloon, when it's all packed together, doesn't get enough buoyant force. Now it's got enough buoyant force, come back here. So when I shrink it down, I pack the molecules more tightly, atoms more tightly. The balloon is smaller, so the buoyant force it gets, which depends only on its volume, shrinks. Its mass, however, is the same because it's still got the same constituents hiding in the balloon. And so it's not a floater anymore. It's heavier than the air it displaces. But as it gets bigger again, everything works out again. You can go visit the ceiling now. Okay? With air, life is a little different. I think maybe you noticed this balloon gets quite small. It goes to much smaller than a quarter of its original size. The helium balloon went to a quarter of its original size because the atoms just got closer together in order to summon up the pressure they needed to keep the air off. That got much smaller. Why? Because the air liquefied, which it violates the ideal gas law. Chemistry occurred. The molecules began to cling to each other. And the result is you can take a balloon like this. Is this going to work? I've never tried this demo. I've got another one to try that we'll finish up with. I should be able to just pack this whole thing in there. I'm liquefying the air. Oh, I'm melting. Well, you get the idea. I want to do the more fun version, which is this. Okay, so it's full of air. I'm not going to seal it for reasons you'll see in a second. I'm going to shrink the air. I'm liquefying it. I'm cooling it down. It packs more tightly in order to balance off the pressure of atmospheric pressure, and then it liquefies and it shrinks even more. And then I add more. I'm going to do this 10 times. I know, it's a lot to watch. Someday it's going to explode in my face. So I'm adding more and more and more mass to this. One of the amazing things is balloons tolerate this abuse. It's really cold, but the balloon manages, this rubber manages to tolerate and bend and fold and not pop, I hope. Bear with me, we're getting close. All right, I'm going to call it, I'll do one more fill and then I'll call it a day. All right. Now, as it heats up, first off, the air, the liquid evaporates and becomes gas, so then it becomes full entirely with gas, and it's out of view from the camera, but oh well. The gas, as it heats up, the molecules travel faster, they hit more often, they hit harder, and they are stretching that balloon skin as stretched as it can get. And the reason to put 10 breaths in there is because it's more reliable at popping. Without 10, it's a little flaky. I had to put it out of our miseries. All right, we'll continue on Wednesday.